Okay? A bomb calorimeter is used to measure change in internal energy. Delta E is internal energy. You might see that as capital U. Sometimes there are different symbols for things. Okay? This is how a bomb calorimeter works. We run our reaction in this very heavy sealed metal container. Okay? It usually weighs 10 kilograms or something like that because it's machined out of a single piece of stainless steel and has a top that screws onto it very tightly. Okay? It's just a real great thing to even hold because it's so precisely machined and really neat. So it has to be tightly sealed, though, because we're going to be producing gases in there, and we can't have any escaping, essentially. So you have a sample in there. Usually it's a combustion reaction that you'll do. So you have your sample in there. You'll usually charge it with oxygen. Okay? You'll usually have excess O2 inside there. And then an ignition wire, and then that's all inside of a water bath that has a circulator, and you can very precisely monitor the temperature of it. So you start the experiment just by lowering that into the water. You carefully measure the water until that's stable. You push a button that ignites what's inside of that bomb there, and any heat given off by that is just absorbed by this water. And the temperature graph will change just like yours did. Okay? It'll go up and sort of level off and then kind of go back down a little bit. So you measure the change in temperature. That's your delta T. Okay? And that's all of the heat pretty much that was given off by that sample, okay? Which you can then calculate. Like we were just talked about, delta V is 0, okay, when we have constant volume. Q, that heat transfer, is a measurable energy transfer for a certain experimental process. State functions like delta E, remember state functions can have a delta, right, final minus initial. They're more general. They're usually given for a balanced chemical equation, or they're given per mole. So Q cal, okay, that would be the heat gained by the entire calorimeter assembly. Okay. That would be the specific heat of the calorimeter, which again would have to be measured in a different experiment. Usually you would take a known process, okay, and then measure the temperature change, and you can figure out what the heat capacity is of that. Okay. So the Q would just be equal to C delta T. Okay. And then just like we did in lab, Q reaction would be negative Q calorimeter. Right? That's because Q system is equal to negative Q surroundings. We can measure the heat gained by the surroundings. Okay, that's the calorimeter. But what we really want is the heat lost by the reaction. Okay, so that's just that sign change there. And then delta E for the reaction, that just puts it in per mole. Per mole of the limiting reactant. Okay. So let's just quickly do one of these. Same equations right there. We have a mass of certain compound, C5H12, that's pentane. It's combusted in a bomb calorimeter. Temperature rises from Ti to Tf. Heat capacity is 6.23 kilojoules per degree C. What is delta E? Qcal, Ccal, 6.23, and let's keep all the units. This one's already in kilojoules, that's handy. Okay. Ccal times delta T. What do I have to do to get delta T in this one? Yeah, which one minus which one? Yep, so that's your 41.23 minus 25.50. Now, if the temperature went down, we would still do final minus initial, but that would be a negative delta T. Okay? So keep your signs straight. Right? Temperature's not always going up. Temperature could be going down, so make sure you're always doing final minus initial. That'll keep your signs correct for even for the heat transfers and everything. Okay? So I got 97 point something, 9979 kilojoules. Okay. That's the heat gained by the calorimeter. Okay. Then what? Ultimately, I want to get delta E. Take a look at our equations. What should we do next? Remember, this was heat gained by the calorimeter, but we're interested in the reaction. Yeah, so Q reaction. So what do we do for that? Yeah, that's easy. Change the sign. That's the heat lost by the reaction. Okay? Don't forget about that. Anytime we're using a calorimeter to measure heat, that sign change has to happen, and probably about half of students forget to do that on an exam, so don't forget that. Okay? Whenever we're doing calculations about the water changing temperature or whatever like that, that's surroundings. We change the sign to then talk about the system. Q reaction, kilojoules divided by moles. Better do 2.14 grams. The molar mass is 72.146. So you could do that separately off to the side, whatever, but I got a pretty big number here, 3.31 times 10 to the 3. So 3,000 some kilojoules per mole. That's a fairly typical delta E for combustion of a hydrocarbon. C5H12 is a hydrocarbon, not too different from gasoline, right? Pentane, hexane, octane, they're just different how many carbons they have. So since it's used as a fuel in combustion reactions, we would hope at least that it would be able to transfer lots of kilojoules per mole. That's the whole idea. And we want it to be negative if it's a fuel, because any energy lost by the system would be gained by the surroundings. That's the whole idea. Okay? This kind of reaction really can only be measured accurately in a bomb calorimeter. Okay? If we tried to measure this reaction in a coffee cup calorimeter, we would be having problems because, yes, it would be giving off heat, okay? But what's the other thing it would be doing? What are the two ways energy can be transferred? Heat and work. Okay? If it was just open to the air, it would be producing expanding gases, and that would account for maybe half of the energy change or something like that. Okay? So any reaction that produces expanding gases has to be performed in a bomb calorimeter under constant volume in order for us to understand the energy transfer. Okay? Unless we also want to measure the work that's done. If we want to do it in some kind of container where we can measure the change in volume against the pressure.